Let us now talk about what happens when the parameter set consists of more than one parameters. So the true parameter theta is a vector of two values, theta 1 and theta 2, and therefore the MLE estimator theta hat would also be a vector of theta 1 hat and theta 2 hat. And here we are no longer interested in just the individual variances of theta 1 hat and theta 2 hat, but we are also interested in something called the variance covariance matrix. So those of you that are not familiar with what is a covariance matrix, what is a correlation coefficient, I request you to please read up on these topics before we proceed any further. So the MLE estimators have asymptotic properties, and it has been theoretically proved that the MLE estimators theta hat are multivariate normal with the mean theta and the standard deviation, which is the square root of the inverse of the variance covariance matrix given by the expected Fisher information matrix. Lots of names here and the sentence is also a little involved. We will soon clarify it. Before that, why is it called Fisher information matrix? That's because it's named after Sir Ronald Fisher, about whom we had discussed earlier. So when we write this expression mathematically, we see that theta hat belongs to multivariate normal of second order. So MVN stands for multivariate normal. Since we have two parameters, it's of the order 2. And that multivariate normal distribution would have a mean and a variance, right? That mean is actually the true parameter theta. And this is again intuitive because over repeated sampling, we would want the average of theta hat to be as close as possible to the true parameter theta. Now, because this is multivariate, now theta hat is multivariate, instead of having individual variances, we have a variance covariance matrix, which is given by this expression, where we see that each individual element of this matrix is actually an expected value of the negative of the second order derivatives, right? Now, those of you that are familiar with the covariance matrix would also know that it is a symmetric matrix. So the off diagonal terms here in this 2 by 2 matrix are equal, right? So MVN2 stands for multivariate normal with two variables, and IE inverse of theta would give the variance of theta, where IE of theta is called the Fisher information matrix. Now this again has the problem that IE of theta, these are expected value of the second order derivatives of the log likelihood functions, and we don't know what these true expected values are. All we have is a sample from which we are trying to estimate this. So since the true value of theta is unknown, the expected information matrix is also unknown, and that has to be replaced by something that we can calculate from the observed data. And when IE of theta is replaced by the corresponding observation from the sample, we call it observed information matrix, which is nothing but these second order derivatives but evaluated at the MLE estimators. So evaluated at theta equal to theta hat, right? So now the variance covariance matrix would be given by nothing but the inverse of this observed information matrix. So Fisher information matrix is replaced by the observed information matrix. So to summarize, we can write theta hat as multivariate normal whose mean are equal to the true parameter set, and the variance covariance matrix is given by the inverse of the observed information matrix, which is nothing but evaluated at theta equal to theta hat. Let us look at a little bit in details about what this variance covariance matrix is giving us. So E11 is nothing but the variance of the first parameter theta 1 hat. E22 is nothing but the variance of the second parameter. And E21, which is also equal to E12, are nothing but the covariance between them. Right. So using these variance covariance matrix, we can now derive the standard errors of estimate of theta hat, and we can also calculate the confidence intervals. So let us consider an example and let us look at the normal distribution. So the normal distribution is given by this expression. When we write the normal distribution as f of y given theta, now here theta is a set of two parameters, mu and sigma square, and we have an expression in terms of mu and sigma square. I have actually expanded this parenthesis, this bracket here, put the sigma square outside of it because this would help in differentiating this expression, right? Because we are to write the log likelihood function. So now, and this is a homework for you, you are to find out what is theta hat, which is mu hat and sigma square hat, from a given sample y1 to yn using the maximum likelihood estimation method. When we actually write the log likelihood function and differentiate it, you would be able to estimate, to arrive at these estimators, and we will see that mu hat is nothing but summation yi by n, which is also nothing but sample average. So the sample average is an MLE estimator of the population average, which is the mean, right? Mu is the population mean and mu hat is the estimator, right? And what we have here is the MLE estimator of the variance. Now here we see that in this expression, this is a square, this is similar to the square of the standard deviation term that we are familiar with from high school statistics, except that in the expression, commonly known expression for standard deviation and variance, sometimes the denominator has an n minus 1. However, when we work out from the MLE estimators, we see that the denominator is n, and this is because this estimator, this MLE estimator of sigma square, is not unbiased, and you can prove this by calculating the expected value of sigma square hat and show that it is not equal to sigma square. So since the MLE estimator is not unbiased and we would want to use an unbiased estimator, to make it unbiased, sometimes the denominator is made n minus 1. So this is not the sample variance but similar to sample variance. It's a biased estimator of the sample variance actually. So when we arrive at the variance covariance matrix, so we write that the parameter theta belongs to multivariate normal distribution with mu, with the expected value equal to the true parameter values, and this is nothing but the observed information matrix. So this is IO of theta, right? And we take the inverse of that and evaluate it at the observed values of theta hat. So when we do all of that, this is what we arrive at. All right. So what we see here is that these off diagonal terms are 0. That means that mu and sigma square, the MLE estimators, their estimators, mu hat and sigma square hat, these MLE estimators are independent of each other. They do not covary. This term here gives the variance of mu hat. When you take the square root of that, you would get the standard error of mu hat. And this term here gives the variance of sigma square hat, and when we take the square root of that, we get the standard error of sigma square hat, and so on.